Hello, this is Nick Nielsen of Grand Strategy, The View from Oregon. Today, I will discuss the globular cluster opportunity. There has been a sudden spate of speculation about spacefaring civilizations in globular clusters. The immediate source of this speculation on spacefaring civilizations in globular clusters was a presentation at the 227th meeting of the American Astronomical Society being held in Kissimmee, Florida, where Rosanne DiStefano of the Harvard-Smithsonian Center for Astrophysics held a news conference to announce research she had undertaken along with Alak Roy of the Tata Institute of Fundamental Research. This presentation has been reported in several articles that I will consider, but first I will review the nature of globular clusters in order to give the listener a sense of what is involved. A globular cluster is a gravitationally bound system of stars that orbits a galaxy, which latter is much larger than the former. Globular clusters are usually about 100 light years across and contain thousands to millions of stars. There are about 150 such globular clusters associated with the Milky Way galaxy. Andromeda, a much larger galaxy than our own, has more than 500 globular clusters. About 20% of the Milky Way's globular clusters have undergone core collapse, when the stars bunch up until they are as close together as Pluto is to the Sun. The stars in globular clusters are very old. The main sequence stars like our Sun have burned out, leaving neutron stars, white dwarfs, slow-burning red dwarf stars, and a few pulsars. Globular clusters lack the star formation processes observed in galaxies as a result of galactic ecology, which involves the remnants of stellar nuclear synthesis and violent supernovae incorporated into later generations of stars of higher metallicity, that is to say, metal content, where metals are understood in the astrophysical sense of being any chemical element heavier than helium. Planets form from protoplanetary disks remaining after the formation of a star, and so share in that star's relative metallicity because of this common descent from a single cloud of dust and gas. In the past, globular clusters were thought to be composed exclusively of ancient stars and were sometimes called fossils of the formation of the Milky Way, or whatever galaxy with which a globular cluster is associated. Recent research, however, has shown that globular clusters include stars known as blue stragglers, now thought to be the result of the interaction of stars within the tightly packed confines of globular clusters. Thus, globular clusters are more than mere fossils of spiral galaxy formation, and their histories involve many interesting astrophysical processes. But, on the other hand, it now seems apparent that globular clusters exhibited rather different galactic ecology than that found within the spiral arms of a spiral galaxy, which has sequential populations of stars of increasing metallicity. Globular clusters have previously been viewed as unlikely environments for life because of the assumption that the appropriate planets for life as we know it would not form. We now have good reason to question this assumption. A report on DiStefano's presentation for the website of the Harvard-Smithsonian Center for Astrophysics quotes DiStefano's colleague Alak Roy as saying, quote, "It's premature to say there are no planets in globular clusters," unquote, as against the view that stars in globular clusters are too old and too metal-poor to form planets. Alak Roy is almost certainly correct in this assertion. Indeed, just a few days ago I noted a recent announcement about the discovery of a planet orbiting a low-metallicity star in a paper titled "The HARPS Search for Southern Extrasolar Planets 39, HD 175607b, the most metal-poor G-dwarf with an orbiting sub-Neptune." Thus we can demonstrate that smallish rocky planets, sub-Neptunes in the terminology of this paper, can form in the planetary systems of low metallicity stars. The paper concludes with the observation, quote, "This discovery may have important consequences for planet formation and evolution theories," unquote. DiStefano and Roy have identified what they call the globular cluster opportunity, which is a result of both the long-term stability of planets tightly orbiting dim red dwarf stars, coupled with the relatively short distances between stars and planetary systems in globular clusters. The stability would provide an opportunity for life, intelligence, and civilization to arise, while the close proximity of other stars and their planetary systems would provide opportunities both for SETI and for international travel within a time frame consonant with civilization as we know it. In the Harvard-Smithsonian Center for Astrophysics report cited above, DiStefano is quoted as saying in regard to the possibilities of radio communication between civilizations in a globular cluster, quote, "Sending a broadcast between the stars wouldn't take any longer than a letter from the US to Europe in the 18th century," unquote. And in regard to interstellar travel, quote, "Interstellar travel would take less time too. The Voyager probes are 100 billion miles from Earth, or 1/10 as far as it would take to reach the closest star if we lived in a globular cluster. That means sending an interstellar probe is something a civilization at our technological level could do in a globular cluster," unquote. This presentation on the globular cluster opportunity at the American Astronomical Society by DiStefano was apparently widely anticipated, as I came across a notice of it as an upcoming event the day before it was scheduled, and I have since watched for the articles that have subsequently appeared. In an article by Keith Cooper on the Astronomy Now website, "Could Globular Clusters Be Home to Intelligent Life?" Cooper quotes DiStefano as saying, quote, "Globular clusters may indeed contain very old, advanced civilizations," unquote. Cooper connects the possibility of very old, advanced civilizations in globular clusters with the familiar idea of ancient super-civilizations, and thus to the recent GHAT survey, that is to say, GHAT, or Glimpsing Heat from Alien Technologies, which scanned the cosmos for the infrared structures of advanced civilizations. This GHAT survey was widely interpreted as searching for a Dyson sphere or a Dyson swarm. As it happens, globular clusters would be an especially good place to conduct a survey for super-civilizations, because globular clusters have a naturally low profile in the infrared, and the inevitable thermodynamic signature of a large, energy-intensive civilization should stand out in clearer relief than elsewhere. In an article by Alexander Witz on the website of the prestigious science journal Nature, titled "Alien Life Could Thrive in Ancient Star Clusters, Densely Packed Stars Might Allow Civilizations to Survive for Many Billions of Years," Witz emphasizes the existential risk mitigation aspect of a civilization in a globular cluster. Ease of interstellar travel would mean the possibility of a civilization having many daughter civilizations, as they might be called, which would mean a high level of civilizational redundancy and therefore survivability. Witz quotes DiStefano as saying, quote, "If there is an advanced society in an environment like that, it could set up outposts relatively easily because we're dealing with distances that are so much shorter," unquote. Existential risk mitigation is crucial for us as well, stranded as we are in the less compact arms of the Milky Way, the difference being that interstellar travel is much more difficult for us among the widely spaced stars in the galactic arms, making it much more difficult for us to establish civilizational redundancy. The closer confines of a globular cluster confer an advantage upon civilizations arising in this context because of the greater ease with which a spacefaring civilization could travel to entirely distinct planetary systems. The article by Keith Cooper cited previously also touched on the existential risk angle. Cooper wrote, quote, "A starfaring civilization building colonies around many different stars has enhanced longevity because it becomes immune to many existential dangers. If war or disease breaks out on one planet, or another colony is hit by an asteroid, the civilization would still survive on other worlds," unquote. Jonathan Webb of the BBC wrote an article titled "Star Clumps Harbor Sweet Spot in Search for Alien Life," emphasizing the SETI opportunities presented by the globular cluster opportunity. Webb spoke to Alan Penny, also at the American Astronomical Society meeting. Penny, an astronomer at the University of St. Andrews and coordinator of the UK SETI Research Network, is quoted as saying of the De Stefano presentation, quote, "I think it does lift globular clusters up in the wish list of targets to search," unquote. In regard to the globular cluster opportunity, it certainly seems that if a spacefaring civilization emerged within a globular cluster, it would have many advantages in making the transition to becoming an interstellar civilization. The arguments of De Stefano and Roy focus on the long-term stability of the environment and the close proximity of stars to each other, which would mean the radio-based search for and communication with extraterrestrial intelligence within more reasonable timescales than we face here in the arms of the Milky Way, and distances between stars that would make interstellar travel practicable at a lower stage of technological development than would be required for interstellar voyages in our galactic neighborhood. And both factors are important in the development of advanced civilization that can pass the spacefaring threshold. Nevertheless, there are potential problems as well. While low metallicity may not prevent the formation of smallish rocky planets, and therefore places where life as we know it could evolve, these planets formed in low metallicity conditions would have fewer of the mineral resources that have been crucial to the development of industrial technological civilization on Earth. Interstellar travel in particular, even across the relatively short distances between stars in a globular cluster, would require advanced industrial technologies that one would expect from a civilization with ready access to elements at the heavy end of the periodic table, including fissionables. Also, the lower levels of radioactive elements in the crusts of such planets would mean that they would cool down more quickly and thus might not remain viable places for life and for civilization over the very long term, as De Stefano and Roy are positing. I look forward to the paper that will eventually emerge from this research, as I will want to see how the authors handle the question of the development of spacefaring civilizations in low metallicity planetary systems. Such civilizations in globular clusters would have great opportunities that we lack due to our relative isolation, but they might be faced with insurmountable obstacles in the development of civilization if the planets orbiting stars in globular clusters have relatively little iron ore, copper, lead, gold, uranium, and other industrial metals. It is the particular galactic ecology of large spiral, and probably also large elliptical galaxies, that results in planetary systems with an abundance of the metals and minerals needed for industrialization. This observation suggests a possible fundamental tension liable to play out in the emergence of spacefaring civilizations. Civilizations in galactic spiral arms have the resources necessary to create a technological civilization, but find themselves too isolated to expand to other planetary systems. Civilizations in more closely packed globular clusters find themselves placed so as to make interstellar expansion possible, but may not have the necessary resources to create a technological civilization. Thus, there may be very old, advanced civilizations in globular clusters, as De Stefano has suggested, but they may be million-year-old or even billion-year-old agrarian civilizations that have been unable to make the breakthrough to industrialization because of a lack of resources necessary to an advanced technology. The motif of a million-year-old civilization occurs frequently in discussions of SETI and super-civilizations, as mentioned above, though this motif usually takes the form of highly technologically advanced civilizations. Imagine for a moment, if you will, a million-year-old civilization that has stagnated in agricultural modes of production. This can be posed as a thought experiment. Consider the possibility of a very old civilization that never experiences an industrial revolution. There are at least two possibilities here, as well as a continuum of possibilities between these two. Firstly, there could be a stagnant agrarian civilization enduring on a stable world for 1,000,000 years or more, and remaining essentially unchanged over this period of time. Secondly, there could be an extremely gradual ramping up of technology in a sequence of civilizational development retarded by the absence of industrial resources. If we think of what we have accomplished in the way of industrialization on Earth since the Industrial Revolution, and then we stretch this process out over 2,000 years instead of 200 years, this gives a sense of a civilization developing at an order of magnitude slower than ours. Perhaps a civilization might even develop at a rate 2 or 3 or more orders of magnitude more slowly than terrestrial civilization. Of course, the idea of a civilization that develops an order of magnitude more slowly than our civilization also suggests the possibility of a civilization that develops an order of magnitude faster than ours, but we will not pause to consider this at present. A million-year-old agricultural civilization might look like an industrialized civilization of a much younger age, perhaps as young as our industrialized civilization, except that this older civilization would have a very long history, which means either a massive archive if civilizational continuity were maintained, or a lot of ruins and buried artifacts of the past if civilizational continuity was not maintained. A very old agrarian civilization that was laden with 1,000,000 years' worth of art treasures would be remarkable, even if it had not made the breakthrough to industrialization. But this thought experiment is contingent upon a very old civilization lacking the resources to experience an industrial revolution, or a civilization experience a slower moving industrialization process. We simply do not know if this will be the case or not. We do not know, and we probably will not know for a very long period of time, the detailed composition of the crusts of planets formed in globular clusters. Such planets may be more likely to harbor technological civilizations that I have suggested here, but it is interesting to note, in historical terms, that the developmental sequence of technology on Earth begins with copper, tin, and iron, moves on to steel, and only in the 20th century did we gain the capacity to make use of really lightweight metals like titanium, which is especially suited for the manufacture of spacecraft. Would a different developmental sequence be possible on a planet lacking significant iron reserves? Or would a civilization never reach the level of metallurgical technology without first having the experience of metals that are easier to work? We must admit that we do not know the answer to this question, but even to pose it suggests the formulation of a research program both for the study of exoplanets in globular clusters as well as for a science of civilization. I will admit that I remain skeptical about civilizations in globular clusters, and my money is on the spiral arms as incubators of civilizations, as they have indeed nurtured the only known instance of civilization. Nevertheless, the globular cluster opportunity is an interesting idea that deserves further study. Thank you.